Hello, welcome. We stand at a critical moment in chemical engineering, a moment where innovation is not just desirable, it is necessary. The world is demanding cleaner, smaller, safer, and more efficient processes. Traditional approaches can no longer keep pace. This is where process intensification steps in, not as a buzzword, but as a revolution in how we design and operate chemical systems. At the core of this revolution is computational software, the driving force that lets us model, optimize, and rethink processes before they are ever built. This presentation, prepared by Group 24, the Chemical Department of Chemical Engineering, Kane University, will explore how these tools are transforming our industry. Process intensification or PI is a strategic redesign of processes to make them more sustainable, efficient, and economically viable. Computational software is what makes this possible, giving engineers the power to simulate, model, and optimize without expensive pilot plans. In this session, we will explore how PI principles, the software enabling them, and real-world case studies, and a look ahead at the challenges and future directions. The essence of PI is straightforward. Create create smaller, cleaner, safer, and more efficient processes. It is not about minor tweaks. It is about rethinking the way we design systems from the ground up. With computational tools, this redesign happens in a virtual environment, cutting both time and cost while reducing risk. Fundamentals of PI. PI follows a few powerful principles: reduce equipment size and energy consumption, enhance reaction rate and selectivity, integrate multiple steps into a single unit, improve heat and mass transfer efficiency. Examples include reactive distillation, spinning disk reactors, membrane reactors, and microchannel systems, each showing how clever design can transform performance. Now, the role of computational software. Without computational software, PI would be slow, costly, and risky to implement. These tools allow engineers to test ideas virtually, explore hundreds of design variations, and predict potential hazards, all before touching physical equipment. They speed up innovation and allow safer, smarter decision making. Modeling and simulation tools. Modeling tools like Aspen Plus, COMSOL, ANSYS Fluent, and DWSIM are central to PI. They allow us to capture complex thermodynamics, simulate chemical reactions, and study fluid flow with precision, revealing design improvements that might otherwise be missed. Now, process optimization. Once a design is modeled, optimization software such as MATLAB, Simulink, GAMS, and Python PyMo or SciPy helps fine-tune it. We can minimize energy use, maximize yield, and find the best operating conditions, even for systems with multiple changing variables. Data twins and Industry 4.0. Data twins make the system even further, creating a live virtual replica of process that updates in real time. Combined with Industry 4.0 technologies, they allow predictive maintenance, real-time optimization, and safer plant operation, making facilities smarter and more responsive. Let's move on to the case studies. Aspen Plus. In bioethanol production, Aspen Plus was used to model reactive distillation, and the simulation achieved 35% energy savings and over 98% purity. a perfect example of how virtual experimentation can deliver real-world efficiency gains. Case study for COMSOL and ANSYS Fluent. COMSOL was applied to hydrogen membrane reactors, optimizing membrane geometry and temperature for better output. Similarly, ANSYS Fluent modeled microreactor flow in nitration, improving mixing efficiency and ensuring safer operations. Case study for MATLAB. MATLAB multi-variable control systems were used to manage a complex heat exchanger by adapting to real-time changes. The system cut energy use by 20% during dynamic operations, proving that smart control was real savings. Now, the benefits of computational tools. The advantages are clear: lower development cost, faster design cycles, greater accuracy and process insight, improved safety through hazard simulation, space for innovation in both equipment and process designs, and better sustainability through optimized resource use. Challenges and future directions. However, there are challenges. High computational cost, steep learning curves, and the need for accurate input data. The future of PI lies in integrating AI and machine learning into simulations, adopting cloud-based platforms for large-scale modeling, and creating more accessible open source tools to widen participation. In conclusion, computational software is no longer optional in chemical engineering. It is the foundation of the next generation of processes. By combining the principles of process intensification with the power of simulation, we can design systems that are cleaner, faster, and more resilient. As upcoming engineers, our role is clear: master these tools, push innovation forward, and lead the way to a smarter chemical industry. Thank you.